In this lesson, we will see how indices are used in maths, and we'll have a look at the index laws. We'll use indices to help us solve this problem. We have ordinary paper that's 0.1 of a millimetre thick, and we fold it over 50 times. How thick will that folded paper be? Will it be the thickness of a phone book, or maybe 10 telephone books? Would it be the distance across a room, or maybe even across Australia? Will it be the distance to the moon, or further again, perhaps the distance to the sun? We'll learn a little bit about indices to help us solve this question. Is there a shorthand way of writing 2 plus 2 plus 2 plus 2? Multiplication gives us repeated addition, so we can write that as 4 times 2. Is there a shorthand way of writing 2 times 2 times 2 times 2? There is, and it's repeated multiplication this time, so we write it as 2 to the power of 4, not 4 times 2. We're not multiplying 2 by 4, we're multiplying 2 by itself 4 times. The base there tells us what we're multiplying, and the index there tells us how many times we're multiplying that 2. Indices are just repeated multiplication. An index is also referred to as an exponent or a power, so it goes by different names. Okay, so let's write these numbers as 2 to the power of something. So jot down those answers, pause the video and have a go at writing those. And so we have 2 times 2 is 2 lots of 2 being multiplied, and of course that works out to be 4. Next one we had 3 lots of 2, so it's 2 to the power of 3 gives us 8. We have 4 lots of 2 being multiplied to give us 16, and then 5 lots of 2 to give us 32. Now what about 2 itself? We have 2, 4, 8, 16, 32 is our pattern there as we go down, and we are multiplying it by another 2 each time we go down. And our powers here are 2, 3, 4, 5. That's the number of 2's that are being multiplied. So following that pattern, what do you think the power would be for just 2 itself? Well, we can see that it would be 2 to the power of 1. We can simplify expressions like 2 to the power of 3 times 2 to the power of 2. Going back to the definition, 2 to the power of 3, of course, means 2 multiplied by itself 3 times. And 2 to the power of 2 means 2 multiplied by itself twice. So altogether we have 3 lots of 2 and 2 lots of 2, so that gives us 5 lots of 2. And it doesn't really matter what the base is. It doesn't have to be 2, and it doesn't matter what the indices are. They don't have to be 3 and 2. So we can generalize this and say, if we have a to the power of m times a to the power of n, then what we do is we add the indices, provided of course that the bases are the same. They're both a. Let's see what happens when we divide. In this example, we have 3 lots of 2 that are being divided by 2 lots of 2. So we can cancel down, and in essence what we're doing is we're saying that we have 3 lots of 2 subtracts 2 lots of 2, which gives us 1 lot of 2. Now it doesn't really matter what the base is, so we'll generalize and we'll call that a. And it doesn't really matter what the indices are either, so we'll just use m and n. So when we divide those two, then we subtract the indices. And of course the base must be the same. Here we're raising 2 to the power of 3 to the power of 2. So the squared really means we're multiplying by itself. And so we've got 3 lots of 2 and another 3 lots of 2, which makes 6 lots of 2. So if we have a to the power of m and then n lots of that, we really have n times m lots of a. We're multiplying those two indices. So let's go back to our paper folding problem, and to answer the question we'll see if we can establish a relationship between the number of folds and the number of layers of paper. To do that we'll set up a table of values like this. If we have no folds we will only have one layer of paper. Once we fold it once we'll have two layers of paper. So pause the video and see if you can fill in that table right through to 5 folds. You can get a piece of paper out and actually count up the number of layers, and then come back and compare your answers with the ones I've got. Did you get these answers? You can see that what we're doing by folding is doubling the previous numbers of layers that we had. These numbers are obtained by doubling the previous number. And so what we would like to be able to do is to work out what this number will be and what it'll be for 50 without having to work out what the previous ones were. So if we work out how many times we're doubling, then we should be able to write this using index notation. So going from 1 to 2 we've doubled once only, and then we have to double a second time to get to 4, and then we have to double a third time there to get to 8, and a fourth time there to get to 16, and we're doubling 5 times there. So when we get to 10 folds we will need to double 10 times. So that's 2 to the power of 10, and of course it'll be 2 to the power of 50 when we have 50 folds. We can of course generalize this and say if we have n folds then we will have 2 to the power of n layers. Now we can work out how far our 0.1 millimeter thick paper will stretch out after 50 folds. We will have 2 to the power of 50 layers of paper, each 0.1 millimeter thick. So we multiply those two together to get the distance. Now 2 to the power of 50 is this enormous number over here, which when multiplied by 0.1 is still an enormous number. So let's change our units from millimeters into kilometers. So we'll divide by 1,000, and that'll give us over 112 million kilometers. So the distance to the sun was the nearest choice. Let's see if we can give some meaning to zero and negative indices. We have a pattern here where the powers are being decreased by 1, so the next one will be 2 to the power of 0. And on the right hand side we're dividing by 2. So the next one will be 2 divided by 2 is 1. That is 2 to the power of 0 is 1. Progressing with this pattern here, our next power will be negative 1. And we have to divide that 1 by 2 to give us a half. So our 2 to the negative 1 will give us a half. Continuing with this pattern, our next power will be negative 2, and when we divide the half by 2 we'll get a quarter. The next one will be 2 to the negative 3, which will give us 1/8. So we can generalize this. Any number to the raised to the power of 0 will be 1. For example, 2 to the power of 0 is 1. And when we have a to the negative n, then we have 1 over a to the n. For example, 2 to the negative 3 we saw was 1 over 2 by 2 by 2, that is 1 over 2 to the power of 3. We saw that index notation is a shorthand way of writing repeated multiplication. The index laws help us simplify our numbers, so with the same base there we can add the indices when we're multiplying, we subtract the indices when we're dividing, and when we raise to a power and then to a power again we multiply those indices. A 0 index gives us 1, and a negative index means 1 over.